The broadcast is now starting. All attendees are in listen-only mode.
Ladies and gentlemen, good afternoon or good morning or good evening wherever you are in the world. My name is Tim Collins and I'm the Secretary General of the International Stainless Steel Forum, and it's an absolute pleasure to welcome everybody today to our second webinar on building bridges for generations. First and foremost, I'd just like to sort of introduce myself and my colleague Joe Class, who's assisting with the webinar today, and also just give a bit of an overview of how the session is going to run. So I've worked for my entire career in the stainless steels industry, so hopefully I know one or two things about stainless steel, covering technical operations and supply chain management disciplines. And I'm originally from Sheffield in the UK, which is one of the three birthplaces of stainless steel, so I guess that's not a complete surprise. During the session today, we will pause partway into the session and then at the end for questions. And there's good reason for having two question and answer sessions. One is to just allow people who are fairly new to stainless steels to ask a few questions about some of the basic understanding points of stainless steels, and then take a fuller Q&A session later. Now, we recognise that we've only got an hour for this webinar, so some of the detailed technical questions we will not have the opportunity to fully answer all of those. However, if people log their questions using the chat button function, then all questions put that way that required a more detailed explanation will be replied to with all the detail that is required. So we're not going to miss any questions, but we won't have the possibility to deal with them all in this 1 hour session. So I trust that's okay with everybody. And just to mention Joe, so Joe is sort of making sure everything runs smoothly and I don't sort of go too far off piste with this webinar, and she'll be facilitating all the questions that are coming in. So I'd like to move forward and just give you an overview of what we're going to talk about today. So first and foremost, I'll give a brief introduction to the global challenge in terms of building resilient infrastructure. And that's a fairly short introduction, but I think will pose some food for thought across the audience we have today. In section 2, I'll provide an introduction to stainless steels, and then after that section, we'll have a short pause to take any questions arising from that introduction. Section 3 will talk about why would you choose stainless steels. And then in section 4, we'll showcase some of the current bridges where stainless steels have extensively been used and talk about why stainless steels were chosen. Section 5 will talk about life cycle costing, which is an important component when thinking about material choices and particularly stainless steels. And then section 6 will have a fuller Q&A session. So the presentation section itself should take about 45 minutes, which gives us some time at the end for a full Q&A session. So I'd like to sort of move forward now, and we'll talk about the global challenge, which essentially is building resilient infrastructure. But first and foremost, I'd like to sort of travel back in time to the birth of stainless steel. And this gentleman, an English gentleman, Harry Brearley, was one of three people who are really credited for the creation or invention of stainless steels. And Harry Brearley is also credited with the producer of the first commercial cast of stainless steel. And he made a wonderful quote in 1913 that was, "Nobody was impressed with my suggestion. Perhaps the idea of producing a steel that would not corrode sounded ridiculous." And I think there is still some of Harry's words echoing around in today's society. People don't often consider stainless steels first and foremost. And there are many good reasons why people don't consider that. But I'll come and talk about some of those features a little later, but just hold Harry's thought in mind until we get into the section on stainless steels. I'd also like us to consider the United Nations Sustainable Development Goal 9, which is about building resilient infrastructure, promoting inclusive and sustainable industrialisation, and fostering innovation. And I think that's a very credible goal that, as a global society, we should all have no issue with, no problem with. However, almost a year ago, Antonio Guterres, the United Nations Secretary General, made a statement that clearly said there is no escaping the fact that the global landscape for the Sustainable Development Goal implementation has generally deteriorated since 2015. And that's a very sad reflection of what's happened all over the world. So I think equally this frames what we are focusing on now, or we should be focusing on for our future to come, and particularly in light of things like the Paris Agreement and supporting the United Nations Sustainable Development Goals. So I'd now like to sort of just pose some questions about how I see our global challenge in this area. And I think it's probably fair to say, not everybody may agree with this, but we've allowed for some time traditional thinking to dominate how we approach infrastructure. And frequently we focus on low-cost installations, contracts awarded to lowest price bidders. It's a very competitive environment. And we've all been brought up with that way of thinking, me included. Excuse me, but ultimately that will lead to suboptimal choices and definitely suboptimal outcomes. And one aspect of that is that maintenance and the associated costs is often overlooked up front. It's seen as somebody else's problem. I think it's equally fair to say that we've ignored pretty much for some years the oncoming environmental warnings. I think probably some years ago there was confusion about them, but we can all see this pattern now, and we can see the dangers the environmental changes are bringing. And I think when you put those two things together, the question I would ask is, has the McDonaldization, in other words, the disposable society, engulfed us all in a not too healthy way? But I think at the same time, it's fair to say that we've also been, as a global nation, extreme innovators. And it's that aspect we really need to draw on. We need to use our intelligence and our resources effectively. So I think in the area of infrastructure, and particularly bridges, our challenge may be succinctly summarized as: we should choose environmentally appropriate materials, we should design for minimal maintenance, we should make once and once only, and that's once for generations. And then ultimately the end of life, and we should be looking beyond 100 years, we should reuse or at least recycle those materials. So that's the frame that sets the direction for the rest of this webinar. And I'd now like to move on and give a fairly brief introduction to stainless steels. And it's important that people recognize the plural here. So let's start with some myth busting. And here are 6 elements or statements about stainless steels that over my career I've had said to me many times. I think the top of the list is unsurprising for many people. They're a very expensive material. So many people have said to me, I can't even think about choosing stainless, it's so expensive. Another common myth is that only 2 grades exist: 304, the 18-8 stainless, and 316, the molybdenum doped version of 304. People aren't aware of what else is out there. And again, I'll come back to that in a moment. Many people say, hey, these products are impossible to work with, they're difficult to form, difficult to machine, really hard to weld. Stainless steels are just too demanding. And then there's always a question about corrosion resistance. People just think they don't rust. And that's great. We like people to think that, but choosing the wrong stainless steel for a particular environment will leave you with a rusting problem or a corrosion problem. So we have to have some knowledge here. Often people are also unhinged by the fact that they believe all stainless steels are non-magnetic. And that's not true. And again, I'll come back and describe that. And one of the most amusing ones that I've found in, and this has been said more than once, stainless steels are only produced in the Northern Hemisphere. Other countries don't produce stainless steels, which of course is a fantastic myth when more than 50% of global stainless steels are produced in China today. And there's many other countries around the world producing significant quantities of stainless steel, including the South America countries, South Africa, Japan, Korea, lots of big players in all these regions. So let's just counter those myths. So in terms of the expense of material, the counter argument, which I will describe later, is we should always think about life cycle costing, because this is where stainless steels will show you a different way of thinking. In terms of the grades, there are more than 100 stainless steel grades in use today, and they exist broadly in 4 separate families of products, which I will describe shortly. Most stainless steels are not difficult to work with. It's all about understanding. They are formable, they're a machinable product. Many of them are just as easy to weld as carbon steels. In terms of rusting or corrosion, you really have to understand a little bit about corrosion and then choose the appropriate grade for the environment. It's like a horses for courses question. You wouldn't choose a horse that only runs on a flat course to jump over fences. And it's the same with stainless steels. In terms of magnetic or non-magnetic capabilities, the family of stainless steels includes magnetic products and non-magnetic products. And it's the austenitic group that we're probably more familiar with that are the non-magnetic family. And as I've said a moment ago, stainless steels are produced all over the world. So having sort of corrected a few myths, let's just talk about what are stainless steels. Well, fundamentally, stainless steels are alloys of iron and chromium with generally very low levels of carbon. And I've listed below that a few of the other alloying additions. That's not an exhaustive list. That's just some of the popular and critical ones. But I think it's very easy to say that stainless steels are really a set of related families of iron chromium alloys, all containing at least 10.5% chromium. And that's a critical content because it's that level of chromium as a minimum that makes stainless steels corrosion resistant. And I'd like to try and just demonstrate this with the help of a little diagram. So if you take this diagram that's now appeared on the bottom right-hand corner of your screen, and we'll work through the diagram from the left to the right. What you have initially is the stainless steel itself as a substrate material with a layer on top. And that layer is what is known as the passive layer, and it's an invisible chromium oxide coating that forms freely on the surface of all stainless steels in the presence of oxygen. The oxygen atoms are denoted by the little spheres. Now, if you take a bit of an instrument to that surface of stainless steel, and in this case, it looks like somebody's taken an axe to it, and you damage that passive layer, all that happens within milliseconds is that passive layer heals. It's self-repairing. So the oxygen present in the atmosphere combines with the chromium and just forms a new chromium oxide layer. And that's fundamentally why stainless steels are stainless. Now, you can do things to enhance that corrosion resistance, which I'll talk a little bit about, but that's the basic principle, and there aren't other materials that behave in this way. This is a very unique feature. So let's now look at the stainless steel families. And I'll start with what are known as the martensitic group. And one of the grades in here is very similar to that Harry Brearley created back in 1913. But this group of stainless products are really described as having high strength, reasonable ductility, but not excellent. They are hardenable by heat treatment, and they have, we would say in our world, modest corrosion resistance. That's still somewhat better than carbon steel corrosion resistance, but in the world of stainless, it's at the lower end of our spectrum. And broadly, we've got 3 families there: precipitation hardening grades, carbon chromium grades, and then carbon chromium nickel grades. Now, moving on from martensitics, we have the ferritic group of stainless steels. Here we have again reasonable ductility, but somewhat better corrosion resistance, and specifically a resistance to a corrosion phenomenon known as stress corrosion cracking. And these are either straight chromium steels or chromium nickel steels. And now, for reasons that will become apparent in a few moments, I'm going to move to the right-hand side of the family tree, so to speak, and talk about the austenitic group of stainless steels. And people will be familiar with these in the forms of cutlery, pots, pans, domestic appliances. But these products have really good strength, they're highly formable, good to excellent corrosion resistance, and they have excellent ductility, even at very low temperatures. These products do not suffer from a ductile to brittle transition as temperatures fall. And there's a broad range of products here with chromium manganese nickel steels, straight chromium nickel steels, which people will have seen as the 1808 or 1810 stamped on cutlery or domestic goods. Then we have the molybdenum enhanced grades like 316, which are often used in more aggressive corrosion environments. And then the highly alloyed family, or the super austenitic grades, which can be used in high temperature, very aggressive corrosion resistant needs environments. Now, sitting in the middle is the new kid on the block, so to speak, the duplex family of grades. And when I say new kid on the block, these grades have still been around for about 80 years, so they're not that new in the scheme of things. But this is a combination of austenitic and ferritic structures in the same material. And what this brings together is the strengths of both of these types of stainless steel. So you have very high strength, good as a minimum to excellent corrosion resistance, good ductility, good fatigue strength. And these are an area in terms of the stainless steel family that is probably least understood by many people. It's still a relatively modest proportion of total stainless sales around the world. And in this area, you have the lean duplex grades, which have the sort of reasonably good corrosion resistance, through to the super grades, which have fantastic corrosion resistance. And I'll demonstrate more about these particular grades shortly. But it is these grades that really have their place when it comes to bridge applications. So I'll just say a little bit more on these families of grades. So the austenitic group, which is probably the biggest and most familiar sector, at an atomic level is based on a face-centered cubic structure where there are many atoms within the cubic array, as shown in the little diagram on the right, with an atom at the center or middle of each of the 6 faces of the cube, as well as at all the corners. And that gives this great sort of ductility performance even at low temperatures. These grades are easy to form and weld, good to excellent corrosion resistance, and non-magnetic. The ferritics, by contrast, have a body-centered cubic structure. So rather than atoms at the center of each face of the cube, there's just one in the center of each cube, as well as the atoms around the corners. And here you get reasonable ductility and reasonable corrosion resistance. So some sacrificing of the corrosion resistance, but again, these are still easy to form and weld, and this is a magnetic family of stainless grades. The martensitic group are really a stretched cube. It's a body-centered tetragonal structure, so similar to the ferritic, but just, as I said, a stretched atomic structure. Here you get a high tensile strength and good fatigue strength, relatively modest corrosion resistance, as I've said. One additional benefit is wear resistance in this family of grades. And as the ferritics are, they are magnetic. And then if you take the notion of austenitic steels and ferritics and combine them in the same alloy, you end up with the duplex series of stainless steels, a mixture of austenite and ferritic structures. And you can almost say this is the genetically engineered family of stainless steels, because this is bringing together the best of 2 worlds. So if we now just move forward, and I'm not going to go through this list in detail, the presentation will be sent out to everybody after the webinar, but I just wanted to highlight some of the key alloying elements involved and what they bring Now, we've already talked about chromium, but the top three, chromium, nickel, and molybdenum, are the three that are going to be the most important in this webinar, because in terms of duplex steels, it's this combination of alloying elements that brings the duplex structures together and allows us to create a family of steels that has amazing properties. So I'd like to say a little bit about duplex steels. Why are these a good choice? Why are they indeed the perfect choice for bridges? As I've said a moment ago, they have many desirable characteristics. First and foremost, the strength of these steels is generally 15 to 30% stronger than the design strength of a standard carbon steel. Their ductility is comparable with relevant carbon steel grades, and they retain their toughness down to -40 degrees centigrade. Toughness values equally are comparable with carbon steel grades. These products are no more difficult than carbon steels to weld. Their fatigue resistance is at least as good as that of carbon steels, and in many cases better. And where this family of grades really wins is in terms of its resistance to corrosion, particularly pitting, crevice, as I mentioned a moment ago, stress corrosion cracking. So those are the real sort of characteristics of duplex stainless steels that make them really interesting. Now, before I go into the sort of why stainless section, I'd just like to pause for a moment to see if anybody would like to have a question or has logged a question via the chat facility. So, Joe, do we have anything so far?
Yes, we have an interesting question here. It says, what is the maximum temperature a stainless steel can withstand?
And that's the question should be, what temperature would you like it to withstand, I think. So because there are so many stainless steels, it's a question of determine the environment, the operating environment, and we will identify the steel. Well, let's just take as an example duplex stainless steels, because we're talking about duplex for bridges. And the normal working range for duplex stainless steels without creating any problems is -50 centigrade up to 300 degrees, maybe 350 degrees centigrade. Above the 350 degree centigrade temperature, you can start to run into problems with embrittlement because of the formation of certain phases within the atomic structure of the steel. And I'm not going to bore people with the detail of that, but all stainless steels have a defined operating range. And there are some of the very highly alloyed family of stainless steels that can operate at much higher temperatures. So it's really a question of what are you looking for, and we can find the answer. Any more, Joe?
Yes. Does a freeze-thaw cycle cause any issues for stainless in cold weather applications for bridges?
What was the cycle? Just describe it again, please.
The freeze-thaw cycle.
Freeze-thaw, right, thank you. I'd missed the word thaw in that. Now, it's an interesting question, which I think is best answered by thinking about what can happen in a freeze-thaw cycle, particularly if to encourage the thawing of snow or ice on bridges, de-icing salts are used. And that in itself can create a problem, not so much for the right stainless steels, but certainly for carbon steels. But really it depends how low in temperature you're going to go. A duplex stainless steel, as I mentioned, will be quite comfortable down to about -50 degrees centigrade. The austenitic family of steels doesn't suffer that ductile brittle transition, so can go much lower in terms of operating temperature. Of course, you're going to get through a freeze-thaw cycle some material expansion and contraction issues, and they would have to be factored in at the point of design. But I think the real problem is how you cope with what happens to the operation of the bridge during the periods of freezing, and then how that's addressed. And I'll come on to explain that in a few moments. Anything more, Joe?
Yes, I think we should take one last one, and then the rest we will answer after the session or later on. What is the weight reduction versus carbon steel because of the strength?
What is the what? Sorry, what was
the weight reduction when you use stainless steel instead of carbon steel?
I think, again, it depends on the stainless steel you choose, because there are so many available and there's a range of different strengths for each stainless steel. The weight reduction that's possible is related to the choice of stainless steel. And you'll see that on one of the charts in the moment that's coming up, the range of differences in yield strength of stainless steels.
Okay, I think we should continue the session now, and other questions will be answered later on.
Okay, thank you, Joe. So why would we choose stainless steels? So over the next couple of slides, I'm going to highlight some of the key features. So first and foremost, you will get a long and essentially maintenance-free service life, more than 100 years. We can't say much more than 100 years yet, because the industry is not that old. It's only 107 years old. So we have no worries up to 100 years, and it's probably going to be much longer, but that's what we can quote with certainty at the moment. Now, stainless steels, if specified correctly, are not susceptible to chloride corrosion, and that includes seawater, brackish water, and de-icing salts, as I've previously mentioned. In terms of properties for bridge applications, particularly duplex stainless steel, you've got this wonderful combination of strength, ductility, good elongation, good corrosion resistance, and good fatigue resistance. And again, it's all about choosing the right grade in the family for the right environment. The high strength grades reduce the weight of, say, concrete required, or even, and I'll show an example when we showcase a few, the need for concrete completely. Stainless steels offer the lowest life cycle carbon dioxide footprint of all steel products, and also lower than that for aluminium and copper. Stainless steels are available in the same product forms that carbon steels are, so it's really just having a different set of products on the same shelves. In terms of design possibilities, because you're dealing with a product that doesn't corrode and looks aesthetically pleasing all the time, you have many different design possibilities. You don't have to hide stainless away in concrete. And the life cycle costs are much lower than that for both other steels and other competing materials. Now, in addition to those points, the usage opportunities give you some interesting design issues to consider. First and foremost, in saying what I'm going to say now, this is not about stainless steel trying to take over from carbon steels completely. That would be crazy. But in critical structures, replacing carbon steels for stainless becomes highly valuable, because then you prevent failures. And if you identify where things are going to corrode, replace them with stainless, you will certainly prevent failures. I've talked about the visual appeal, and it's a great case in point is the Chrysler building in the USA, which has had stainless steel cladding for almost 100 years and has been washed twice with a normal household detergent. That's all it takes, nothing more. Now, I know that's not a sort of load-bearing structure, but this is just an indication of these products don't need much maintenance. Stainless steels offer a complete rethinking of traditional designs, and some of the bridges we showcase will show what's definitely possible. And there are many stainless steel grades available, as I've said, more than 100, and the duplex family alone is the optimal choice. It's also fair to say that stainless steels globally are produced with about 65% as a minimum recycled content, and when you actually go to the larger producers, that recycled content is above 80%. These products are fully recyclable at the end of life, so with no loss of material integrity. And this year we now have out for public review the new AISC standard, AISC 370 for stainless steel in construction. And the link to this is within this presentation just below. And of course, everybody will be able to sort of reference that once the presentation is circulated. So that's in a nutshell a lot of reasons why choosing stainless steels would be a good thing. Well, let's sort of just try and expand on that. So in this chart, we are looking at the 0% proof strength of mainly stainless steels, but carbon steels included for completeness, against what is known as the pitting resistance equivalent number, which is a measure of corrosion resistance primarily caused by chlorides. And I've put a red line on there that is a sort of chloride corrosion threshold or indication of where you get poorer corrosion to the left and excellent corrosion resistance to the right. And what you see here in this chart is carbon steel has an excellent proof strength value, just shy of 500 megapascals, but that's very comparable with the duplex family of stainless steels to the right. And you can see as you move into the more higher duplex stainless steels, the resistance to corrosion improves dramatically. So here, thinking about the duplex family, you've got the combination of really high strength and excellent corrosion resistance. Now, shown in the center of this chart are other stainless steels, and these have lower proof strength, but a fairly wide span of pitting resistance equivalent number, which means their corrosion resistance is somewhat variable. And you have in there a combination of martensitic grades to the left, ferritic and austenitics in the midsection, and then 316L more to the right. But these grades, when you're looking for high strength applications, are not the bunch of stainless steels you would normally look first and foremost. It is the duplex family that are more interesting there. Now, if I then move forward to consider elongation against the pitting resistance equivalent number, we get a slightly different picture here. So carbon steel and duplex steels are reasonably aligned in terms of elongation, duplex slightly better. But again, we know that the corrosion resistance of the duplex family is much improved. And then you get a separation of the mid-band of stainless grades. So the elongation of primarily the austenitic group is much better than the ferritic and martensitic group. And I think that's one of the features of austenitics. These are very ductile, very formable products, but you have to accept that there's always a trade-off here. You can't have perfectly all the properties all of the time. So what I'll now try to do is bring those characteristics together in a simple diagram. So first and foremost, and this is the same layout as the previous charts, we've got the pitting resistance equivalent number along the bottom, yield strength on the left-hand side, elongation now on the right-hand side. And in the bottom right-hand corner, you would have what I would describe as fictional grades, a combination of excellent corrosion resistance with poor elongation and poor yield strength is not a greatly compatible mix of three things. But then in the bottom left, you have what I would term, when you're thinking about particularly bridge building, unsuitable grades. Here you have a much higher risk of premature failure, particularly in chloride-rich environments, and carbon steel sits in there, sure, as well as some of the classic stainless steels. You then have, in the sort of top left, the dilemma grades. Still, the corrosion resistance is not great, but you have good strength and good ductility. And here you see the sort of manganese austenitic grades and the 18-8 doped with nitrogen to improve strength. But then we get to the final box. What I would say is really the suitable family of grades. This is where you get the possibility of significant weight reduction due to higher strength, excellent corrosion resistance, including resistance to the classic 3 corrosion mechanisms. And you have broadly the duplex family and the higher alloyed austenitics in this box. So that's really the target box when you're thinking about structures that are load carrying and also in corrosive area or corrosion environments. I'd now like to move on and just consider some sustainable credentials, particularly of duplex stainless steels. And for this family of grades, new production contains at least 65% recycled content. In terms of primary energy demand, this family of grades is much lower than that equivalent for carbon steels. The life cycle CO2 emissions of 1.1 tons of CO2 per ton of stainless steel, again, is significantly lower than the carbon steel equivalent. And that's primarily due to the fact that with carbon steels, looking over the life cycle, you'll have to replace the carbon steel more than once. Life cycle costs are significantly lower, and I'll touch on life cycle costs at the end. The maintenance costs are exceptionally lower, even zero. And what's also interesting from a maintenance perspective, because the maintenance need is not there, you take away secondary carbon dioxide emissions that impacts from regular maintenance. So, for example, increased greenhouse gas emissions from standing or disrupted traffic flows, which I'm sure we've all experienced at some time. And then, as I've said previously, these products are fully recyclable at end of life. And that's just the same for carbon steels and aluminium equally, for example. So I'd now like to move into section 4 and showcase some of the bridges. And the particular example here is not a true bridge, but it's one of the runways at Tokyo's Haneda International Airport, which is a very impressive structure out at sea. But in terms of this section, what we'd like to do is showcase 6 bridges from around the world. And for each of the bridges, we'll explain the stainless steel grade or grade selected, the bridge components in which stainless steels were used, the stainless steel products that were supplied from the manufacturers, and the primary reasons why stainless was selected. Now, in all cases, both longevity and minimal maintenance were prime considerations. And within the ISSF brochure released this year on bridges, all these examples are available for further study, and that link will be provided again after the webinar. So we'll start in the Spanish island of Menorca with the Cala Galdana bridge. And this bridge was built using 2205 duplex stainless steel, which is one of the standard duplex family of grades. The stainless components with the load-bearing arches and the support beams, and this was supplied as hot-rolled plate. And this is an example that demonstrates that when considering bridge building with stainless steels, we're not just looking at long products like reinforcing bar. Flat products have a big role to play as well. Now, why in this case did the designers go for stainless steel? First and foremost, the high strength and good ductility, the good corrosion resistance in coastal applications, low maintenance needs, longevity, which I've touched on before, but also the really strong environmental footprint of these products. I'd now like to switch to Sweden, to a very attractive bridge, the Folke Bernadotte bridge, which was made completely out of 2101 lean duplex. So the whole structure here is made from stainless steel. And this is a combination of hot rolled plate, cold rolled sheet, and tubular products. And the reason stainless steels were chosen here was the superior mechanical properties, again, of a duplex family of grades, the need for a maintenance-free life, and the low environmental footprint. And this is quite an attractive bridge, which provides a nice link over the water, and this shows one of the sort of design appeal features that stainless can bring to bridge construction. Now here we have, moving into Japan, a very symbolic and impressive bridge, the Giboshi-bashi bridge, which you'll see from the photograph looks like a wooden construction, and it is. That's absolutely true. But below the waterline is the stainless steel structure that holds this thing together. And this is a Japanese grade similar to a 2205 duplex. and the stainless components, as I've said, with the whole structure below the waterline. And this is a combination of hot rolled plate and bars. But this was a way of ensuring that this beautiful bridge was preserved for many generations by having the critical components below the waterline made completely from stainless steels. And here, the key reasons were, again, mechanical properties, the durability, the corrosion resistance, the need for a maintenance-free life. It's an underwater application, and the excellent corrosion resistance within that application. Our next example is the stunningly beautiful Helix bridge in Singapore, which has a nod of the hat to the double helix of DNA. And this was built with 2205 duplex, and the components made from stainless steel with the hoop members, the deck beams and columns. And this is a combination of stainless plate and tubes. And this has a very interesting feature attached to it when we get to the why stainless section. Some aspects that we've already touched on: the mechanical properties, the high fatigue strength, life cycle costing, maintenance-free life requirements, and excellent corrosion resistance. But the impressive thing here was that the weight reduction that stainless steel allowed made the material costs for this bridge equal to that of using carbon steel. So in this case, it was no more expensive. It was really an exploitation of the properties. And I think that's an important notion to carry forward. Our fifth showcase bridge is a railway bridge, the Anorga bridge in Spain. And this was a location that had very extreme weather conditions. So it was made from 2205 duplex. All the structural components were made from stainless steel, and the primary supplied product was hot rolled plate. And the reason stainless was chosen in this case was, again, the mechanical properties, the need for a maintenance-free life. This is an important railway connection. The operator didn't want downtime, and the excellent corrosion resistance. And this is an environment where you get pretty lousy weather for a lot of the time. I think it's 4 good days, 4 lousy days, 4 very lousy days, and then it repeats. So a good sort of use of stainless steels to ensure ongoing continuity of a vital railway link. And our last showcase bridge in this section is the University Steam Bridge at Birmingham in the UK. And this is a slightly different example where the stainless steel has been selected as a cladding product. And what you've got here is a use of 316L, which is an austenitic grade, and it's laser profile sheets used to clad the bridge. This location, which crosses a railway, a canal and a footpath, was a very difficult to access location. So the reasons why stainless was chosen was, A, the aesthetics. It's very appealing and striking as an imagery feature. The superior corrosion resistance that a more highly alloyed austenitic grade brings, but also the need for a maintenance-free life. This location was considered very inaccessible, and so the designers wanted to be able to sort of fit and walk away, which fits all the requirements of building sustainably. So now I would like to move on to the sort of fifth section, which is about life cycle costing. And here I hope to dispel some of the myths about the cost of stainless steel. Well, let's look first and foremost at the 4 aspects of life cycle costing. And they're succinctly put as the cost of acquiring the materials. So that's the cost of securing the materials and products for a specific project and their installation, and it includes delivery to the installation site. Then you've got the costs of actually installing the materials on the site, then any ongoing maintenance costs to deliver an acceptable operation. And then there is an income stream that either comes from end-of-life recycling of those products or income from sales. And that can include, if it's a bridge, you charge people to cross the bridge, particularly if there is a significant commercial advantage for having the bridge in the first place. Now, when you look at how that looks in relative terms for carbon steel versus duplex stainless steel, you get a very interesting picture. It will be of absolute surprise to know people, I think, in the audience today, that the acquisition costs of duplex stainless steel are significantly higher than those for carbon steel. The installation costs, though, for carbon steel are higher than those for duplex stainless, and that's because you will have to do this process more than once with carbon steel. You won't get the life out of a single installation, and that knocks onto the maintenance costs, which for a carbon steel will be huge, and for a duplex stainless will be incredibly low. And then you get some level of income from recycling at the end of the process. But what you've typically got here is a 20% lower life cycle cost for a duplex stainless steel compared to a carbon steel. And that sort of relationship maps out each and every time for all the projects. In some cases it's a little more, in some cases it's a little less, but it's of that order. So you're spending a little bit more money up front, but you're not spending after that. That's the basic message here. So if we just consider that in terms of material differences, carbon steel acquisition costs will occur at least twice in 100 years of service life. In some cases, that will be more than twice, but we work with twice for prudency. For stainless steel, you do it once and once only. Installation costs will reflect the acquisition differences. So if you have to acquire more than once, you'll have more installation costs. Maintenance costs for stainless steel will kick in. I've put notionally 5 years after installation. In some environments, that will be shorter, that period. And the interesting thing is that corroding carbon steel, particularly as rebar encased in concrete, ultimately causes spalling of the concrete. So you have a hidden dilemma. You don't initially see the corrosion effects taking place because you've hidden the product that is corroding. And maybe, you know, the thought is that in hiding it, you're not exposing it. Unfortunately, concrete is somewhat porous and chloride ions will find their way to diffuse through the concrete. The maintenance costs of stainless steels will always be low. And as I've said earlier, simple cleaning is often all that is needed. Now, we have a real life case study, and this is based on the Progreso Pier and Causeway in Mexico. And if we look at the left-hand side, you can see in the photograph at the bottom, a large causeway on the right-hand side of the photograph and a smaller pier on the left-hand side. And the causeway was built in 1941 using 316L austenitic stainless steel rebar. And in 1969, the additional pier was built using carbon steel rebar. And then if we roll forward 40 years and look at essentially the same photograph, the older large pier and causeway is still perfectly intact, and the smaller pier has pretty much disappeared. So this is a perfect example, and I know it's a marine environment, that in this sort of environment, you don't get a very long life when you're choosing a product that is going to corrode. If we equally look forward at the comparative life cycle costs here, we'll see some interesting differences. Again, maintenance differences are huge. You put carbon steel into these environments, you're going to have a huge and ongoing maintenance bill. And this was, you know, based on 40 years. With the choice of stainless steel, you get very low maintenance completely. Yes, acquisition costs slightly higher, but it's really in maintenance that you win and lose when considering things in this manner. So I'd now like to sort of wrap up before we go to questions with a handful of conclusions. There is no doubt that stainless steels are a superb material choice, particularly the duplex family of grades. That's not to say that carbon steels and other materials don't have a key role, they absolutely do. But the failure of many bridges using carbon steels, and particularly the components within those bridges, can be completely predicted. So it's about knowing the elements within each structure where corrosion is highly likely and dealing with that. Stainless steels bring together lots of desirable properties, but also with the impressive aesthetic. So you can think differently and use your stainless steel to show off the bridge. Because these grades create this opportunity to think and design differently, it does give the opportunity to either eliminate or reduce concrete in bridges. And we have to remember that the concrete, or the cement and concrete industry, is the biggest creator globally of greenhouse gas emissions. So things will never not need cement and concrete, but we can think differently and improve our environmental footprint on the planet just by thinking stainless in the right areas for the right components. We know that the corrosion resistance of stainless steels is generally excellent, but it's about choosing the right grades for the right environments. And one of the appendices that is attached to this presentation, I'm not going to go through the appendices because it's much more detailed technical stuff, will explain what grades are appropriate for different operating environments. It's important to note that life cycle costing is a key component. We need to transform our thinking from low cost installations to life cycle thinking. Let's use our resources wisely, let's make once. And the environmental footprint of stainless steels is equally compelling and should never be overlooked. So that summarizes the elements of this afternoon's presentation. And I'd now like to sort of open the floor to questions. Joe, do we have any that have been logged already?
Yes, we do. The first question is, do stainless steel reinforced structures have a better earthquake resistance than carbon steel ones?
I think, again, if you're looking at the duplex family, and it's an interesting question because there have been lots of developments in recent years about the seismic resistance of stainless steel components. So the simple answer is yes, they do. Again, it's about choosing the right grade for the right environment. But the Japanese producers of stainless steel and the key users there have done an immense amount of work recently on the use of stainless steels for many applications that will withstand extreme seismic activity. And I think that the Japanese Stainless Steel Association probably have some excellent case studies to illustrate that with. So I would say that Japan, probably closely followed by Korea, are two of the areas who've done a huge amount of work in this area. But the simple answer is yes, you get a huge benefit.
Okay, the next question has a kind of a small story. It says, over 20 years ago, I was specifying 316LN and duplex 2205 as options for concrete bridge deck bar, rebar for several projects that I was managing. Now that there is more information available, are there any negative issues with the 316LN as rebar?
Okay, so 316LN is a much higher strength version of 316L due to the introduction of nitrogen. What you will find is that it's really a question of assessing whether that product is more appropriate compared to one of the duplex grades for the application. So there's no doubt that 316LN from a strength perspective will be a good choice, but it's whether it will give you sufficient corrosion resistance over the projected life, or whether a duplex grade is a better choice. You will undoubtedly get the strength from both of those grades, but I think it is a question of looking at the conditions that you need to satisfy and then choosing the most appropriate grade. And now there is that information, as has been pointed out, available. If that's an area where people as individuals feel less comfortable themselves, the ISSF can offer that support. I'm not going to rule out either of the grades as being suitable, because it's a question that both could be suitable or one more than the other. Really, let's look at the set of requirements and then take the most appropriate decision. And it might be there's another grade out there that is more suitable. So it's really about understanding the environment, and let's sort of make the right choice against understanding the need.
Okay. Next question is, what is your view on UNSS 41003 or 3-chrome-12 to be used as a structure member for a bridge?
3CR12 is a wonderful product. It brings a lot of interesting characteristics, but of course it doesn't have the wonderful corrosion resistance of duplex grades. So it really is a question of saying this grade could have a perfectly good use in the right environment. There's no sort of immediate concerns if the right checks are done for a 3CR12, and it has been used in some bridge applications already with good effect. So it is a reasonable choice, but it's again writing down all the conditions that are required and then assessing whether the grade is appropriate. Once you have that information, you can make the right choice, but there's nothing that can be ruled out. It's about having knowledge of the operating environment and the operating conditions.
Okay, thank you. Then is a question about the LCC comparison in the presentation. Is the relative LCC comparison considering painted carbon steel? How would it change if we compared stainless and weathering steel?
It doesn't really change a great deal. I mean, if you have painted carbon steel or galvanized carbon steel or epoxy coated carbon steel, ultimately when these things are bent or start flexing, the coating is damaged, and they will damage over time. All you are doing is slightly slowing down the corrosion process. You're just making it a little bit more hidden, and I think the fundamental question is, if you're going to use a product that will corrode, do you really want to hide the fact that it's going to corrode? Because that leads you to a set of bigger problems when you start to observe the corrosion. So yes, they have a benefit, but it's not, if you're designing for 100 years plus, it's not going to change the impact in terms of life cycle costing by any significant amount.
Okay, and then are there any advantages of stainless steel in front of cotton steel in non-aggressive environments?
Nice question. That's an interesting one. When you're in non-aggressive environments, you don't necessarily need to consider stainless steels. You know, it's really a question of picking the right material for the application. Of course, if you want to design something that is more visually appealing, stainless does come with an attractive shiny look that other steels often don't. So it's really a question of what do you want to do. If you don't need significant corrosion resistance, then I wouldn't advocate choosing stainless. But if you do need a degree of corrosion resistance and all the other properties you'd get from a good general steels product, including Corten, then choose that. You know, it's really a horses for courses choice. But I think what we've seen, certainly as stainless producers, is that sticking things in seawater is not good if you have a steel that's going to corrode. So if it's an environment where you've got no corrosion issues, stainless shouldn't be advocated unless you want to look highly pretty.
The next question is one that is based on the presentation, and it asks, what do you consider as income in the LCC?
Okay, yeah, and I think that always is a question that confuses people. So there are two parts to income. The obvious part is at the end of the life, you can recycle it and you can get paid for recycling it, and that should not be overlooked, because lots of metals are fully recyclable, and we should try and recycle as much as possible, because that avoids digging things out of the earth, which is not good generally for our planet, and it's certainly not good for our CO2 and other greenhouse gas emissions footprint. So recycling is a highly positive thing, and the recycler industry does a great job, but still has some way to go to recycle more. There are still things that are not being effectively recycled, and we need to develop that area too, because the greenhouse gas emission benefit you get from recycling is huge. So it's important that we do that. But then the other income stream is whether in the creation of your concept, you can actually generate some income. So for bridges, the obvious one is tolls. If you create a structure that eliminates a very long journey by train or road, for example, you can charge for that. And that's an income stream that goes against your life cycle cost, because if you can take 30 minutes, 1 hour off somebody's traveling time, that's worth something, and people will pay for those things. So in this example, that's what's meant, those two aspects are what are meant by income.
Okay, thank you, Tim. I think we can take one last question, and the other questions we will answer by email, if that's okay. So it says, sometimes we cannot identify the reason of corrosion. Is it possible to calculate the range of corrosion allowance?
We can't identify the what of corrosion, Joe? Just say that first bit.
The reason for the corrosion.
Reason. Okay. So, I mean, that's an interesting question, because I would argue if you know the operating environment that you're going to put something in or build something over, then, and you know the materials that you are choosing, then you should be able to predict the corrosion mechanisms that are most likely to occur. And certainly within the ISSF, we have some good information on that from both a stainless perspective, but also a combination of using stainless steels and carbon steels in the same structure. So I would argue it is possible to predict, but you have to know the environment. And that's where really thinking about this up front is really important, because you can save yourself a lot of heartache and pain by understanding the environment and then choosing the appropriate materials to avoid corrosion in that environment. And we have to remember, when I talk environment, there might be components within a structure that are operating in a different environment to other components in the same structure. So it's not one environment for one structure. You could have many micro environments affecting the same structure, and that level of understanding is important.
Okay, I think we can end the Q&A session here.
Okay, thank you, Joe. I hope for the people that asked those questions, the answers were helpful. Like many things, sometimes the answers include a set of other questions, but I hope that at least put things in perspective for people. As Joe said, all of the questions we will answer by email. Everybody who's attended the webinar will get this presentation and the associated helpful links to other information. And as I sign off, I'd just like to leave everybody with a couple of thoughts from two of my sort of favourite people around the world. Sadly, both of them no longer alive. But the great William Edwards Deming said, we don't have to necessarily think about change because survival is not mandatory. But I think we do have a responsibility to our children and our children's children to ensure that everything does survive. And also the great Peter Drucker, who I met once, he said, the greatest danger in times of turbulence is not the turbulence, it's to act with yesterday's logic. And I think we sit at a crossroads where we have the opportunity to now use today's logic, and let's abandon yesterday's logic. So thank you everybody for listening. I hope it was in some way informative, stimulating and thought-provoking. And as I said, we'll answer all questions in due course. But equally, if you have questions that you think about after the event, my email address will be linked within the presentation. Please email us and we'll answer everything as well. Thank you very much. Goodbye.